Society, Australasian chapter. As always, I start with a quick introduction and then we go to the webinar by Eric Blond. As you can see here, Australasian chapter is basically covering Australia, New Zealand and South Pacific Islands. So we have almost 45 chapters around the world. IGS, the International Geosynthetic Society, more than 4,000 individual members, 500 student members, and almost 190 corporate members. So it's a global society. Then, as you know, we have lots of events throughout the year. We do a lot of seminars. We did a geomembrane workshop, 2 days in Melbourne and 2 days in Brisbane just last month. And also, as part of your IGS membership, when you become a paid IGS member, you get access to two prestigious journals. The first one is Geotextiles and Geomembranes, and the second one is Geosynthetics International. I decided to show you guys quickly how to access the journals, because I had a few people recently asking me how to access the journal papers for those two geosynthetic journals. So basically you will need to go to the IGS website, which is www.geosyntheticsociety.org. Then you go to the login section to register. If you recently joined IGS, you will get a IGS membership number, and then you create your login details with username and password. So you join, you basically log in as a member into the website, and then what you need to do is you need to go to the technical resources section up here. Click on that and choose journals, and it takes you to the journals paper, journals page. So you'll see here we have two tabs, one for Geosynthetics International and another one for geotextiles and geomembranes. You go to the IGS member access and click on the link that takes you to the IGS journals. If you have chosen Geosynthetics International, for example, that's what you will see. And normally on the left-hand side here, you need to scroll down and basically you will see all the previous issues of the journal. And you can search or you can choose based on the year that the paper that you're looking for is published, and you can find it there. The full paper is accessible. Also, our Australasian chapter website, www.acigs.org, and we have lots of resources, and we sort of adding to that resources section as we have more webinars and workshops and seminars. And then also the membership tab here, make sure every calendar year you renew your membership. It can be individual or through your company. In the resources section, one important addition we've had is the recording of our lectures. And you'll see examples here by Professor Tim Stark and Professor Zornberg. For example, we also record the webinars and upload them to our website, and they are accessible for today's webinar. We thank our sponsor, Red Earth Engineering, a consultancy company, and they have sponsored this webinar. We thank Red Earth for their sponsorship. And the topic for this webinar is designing geocomposite drains for long-term applications, and it's being presented by Eric Blond, a professional engineer who lives in Quebec, Canada, and is joining us from Quebec tonight his time, I think 8 p.m. or somewhere around that time for him, and it's morning for us in Australia. Just a quick bio of Eric. with more than 25 years of experience and projects conducted in Canada, USA, South America, Europe, and the Middle East. Eric Blond holds one of the most comprehensive independent expertise in geosynthetics and other polymeric construction materials. Eric Blond offers technical services to the geosynthetic and engineered construction material industries, from engineering services focused on application of innovative products and technologies to forensic investigation and serving as expert witness. Eric has an in-depth knowledge of the usage, limitations, and opportunities offered by synthetic materials used in construction industry. And I finished with a photo of Eric just last month, spending time in Australia. This photo is the workshop we held in Melbourne. And thank you, Eric. I'll stop share from my side and I'll get you to start your presentation.
Thank you. Okay, so I'm not mute. Everything is perfect. So share screen, and I think I should share this screen here. So can you confirm that you have the right information on screen?
Yes, it's all good.
So you have the screen with ACIGS webinar and my front page, the front page of my presentation.
That's correct, yep. And
the sound is working well.
Loud and clear.
Loud and clear, super. So okay. Thank you very much. It was a very nice introduction. I would like to mention as well that I've been elected twice on the IGS Council, so I'm very committed to the industry, to the development of the industry. I found my reason for living in these activities. So here, today I'm going to try to give you a short presentation, well, it's short, so something close to 1 hour, on the design of geocomposite drain for long-term applications. And I think we're going to finish that with a question and answer session. So that is very interesting. I look forward to that. So first, a quick introduction, typical application for drainage geocomposites, design geocomposites with index and performance testing, short-term properties, definition of reduction factors, some other design concerns I'm just going to mention, concluding remark, and question answer. So first thing first, why do we need to drain soil? I think most of us here, and I count myself in there, are geotechnical engineers. So I don't think I need to go very far in this description. Soil have a very different behavior depending on their water content, and drainage is the essential tool, essential mean to control the properties of soil. So this photo has circulated on the internet as a fun photo showing a road in Siberia. I don't remember the complete story. So you see, obviously, these people here are posing for the photo. And it's a total disaster, but what I want to show here is really the impact of excessive water content on soil, and you don't go anywhere with that. Much more not fun photo is a veneer in a landfill, where you see here that an excessive rain, well, rain in excess to the capacity of the soil to absorb it, provoked some erosion on the slope, and basically the lack of drainage or insufficient drainage led to a disaster on this project. One thing which I like to mention as well, drainage is going to be working because of the contrast of permeability between the drainage material, the drainage medium, such as the geocomposite, and the soil to be drained. This concept has been known forever. But I like to mention that the name French drain that many of us know has nothing to do with French people. I'm French myself. I was raised in France. And in French, we say drain français, which means French drain. Except that the French drain comes from Mr. Henry French, which was an American person. He was a lawyer by trade, and he occupied several positions in agriculture management at the political level and corporate level. And he's such an American guy that his son is actually the sculptor who carved the Lincoln Memorial in Washington. So that's how far from being French that the French drain is. It's really a very American source. The origin of French drain are completely American. So that's the fun part. And those of you who are very familiar with filtration will have noticed that on my photo, which explains the principle of the French drain, geotextile is badly missing. With such a big gravel, big coarse gravel in contact with the fine grained soil, you should have a filter. You must have a filter. The drain will work only with contrast of permeability, but a contrast of permeability which is going to be maintained over time, which means the stone should not be contaminated. Using drainage to maintain the quality of structures is something which has been known forever. If we look at the design of ancient Roman roads, they would always include a very complex structure made of different sizes of gravel to make sure that structurally it's sound, but also that it's going to be properly drained to avoid loss of bearing capacity because of excessive water content. So these, on the left side here, this 2,000-year-old road, which is near Rome in Italy, is still usable today. So of course, it's not asphaltic material, it's stone. I don't want to be part of the slave team who did install this this road, but yeah, it's been there for 2,000 years and going, thanks to an excellent drainage and probably a little bit over design on the structural side as well. So why should we use geosynthetic drain more than gravel drain? I think all these issues here are going to be more and more important as time goes, as the world is growing. First thing first, and the most obvious one, drainage. A geosynthetic drainage layer is very thin. It's somewhere in the range of half an inch of thickness, a couple 1 centimeter, say, or less. And so it saves space. It saves space. It means less excavation to do on the job site. You don't need to dig a road deeper to be able to have a performing structure, and so on and so on. In the landfill, you also save some storage volume, and so on. It's very practical. A geosynthetic drain can be purchased from a book, from a supplier. It can be delivered on a pickup, on a truck, and it's very consistent. You will always have the same property on and on year after year. When you order a product with specified properties, that's what you're going to get. You don't need to address local variability of stone, of gravels from one region to the other. It's a consistent, convenient product available for installation. The next one is something that I'm not sure everybody is really aware of that. Sustainability, and sustainability not in the sense of greenhouse gases, which is coming after. Also with the fact that sand, which sand or maybe gravel is a bit different, but sand, which is a very common material used for drainage, is among the less renewable resource on Earth. There are some regions for which sand is absolutely not a problem. If you go to the Middle East, in Sahara and so on, you have zero problem finding sand. But if you look at other side of the world, other region of the world, sand can be a very scarce resource. If I look at the situation that I know the best, which is in Montreal, next to my home, Montreal, Quebec, Canada, we have to drive 50 to 60 kilometers to find the next sand pit, and that can be more than that. So building a structure and specifying sand will have definitely an impact on the long run. There used to be sand close to Montreal, but all the pits are gone. They've been used completely. And this situation is going to be more and more critical as the years go by, because obviously any granular material is probably the less renewable material on Earth. Once you have used all the marble from Italy, you don't have any marble anymore. I mean, for tiling and stuff like that. Once you have used all the sand in a region, you don't have any sand anymore. And it's going to take millennial, tens of thousands of years before it comes back. So oil, in a way, is far more renewable than any granular materials. So that's for sustainability. Another one which I think is worth mentioning is gravel puncture. When you install a geosynthetic drainage layer, you have a relatively soft and soft with respect to puncture. A nice material to install against a geomembrane. So when you do lining projects and you have to have a drainage layer, if you have to choose between a gravel which can puncture the liner or a geosynthetics, obviously the geosynthetic is going to be much better with respect to the long-term behavior and puncture resistance, survivability of the geomembrane. Another one is constructability. So there are many applications now where we do have a need for vertical installation of drainage products. Walls, retaining walls, I mean, tunnels, building foundations. All these structures require a vertical installation of a drain, which cannot be provided with gravel. Or it can be provided with many complications. And finally, the last one and not the least, greenhouse carbon emission. What some studies I've read, and it's been replicated by many, have shown that it's up to 5 times less carbon footprint. The carbon footprint is up to 5 times less for a drainage product compared to a gravel material. So if you, I guess everybody is getting more and more familiar with the carbon footprint concepts, sometimes much more than me actually. But if that's the quantity of carbon which is mobilized when you consider manufacturing of a product, transportation, and installation. So all the energy consumption and material consumption that you're going to mobilize to deliver a function on a given site, given application. So all these features make geosynthetic layer far better than gravel layers for drainage. And so yeah, this industry has to grow and will grow because of these essential features which are very important. So what is the structure of a drainage geocomposite? That's what we're going to discuss today. First thing first, there is a drainage core. So again, to work well, drainage material is working on the contrast of permeability. The drainage core is offering a very high permeability. So it's going to capture the water which is around it and is going to transport it to another location. And finally, there is a filter installed on both sides of this drainage media, which is laminated to it and which is going to avoid this void to be filled with soil material. There are many different products available in the market, and that is getting commercial in the sense that many manufacturers have different approach to drainage. All of them want to have this this cavity preserved by 2 geotextiles, and there are different structures. First one, the most common, is the use of a geonet, biplanar, triplanar geonet. Second one is three-dimensional boxes. That's another solution. You have geomats as well, which are random filter. It's like a non-woven with very coarse fibers, which offers open cavity. You have a small pipe, multilinear drainage geocomposites, where pipes are installed between 2 geotextiles at a distance between typically 25 centimeters to 2 meters for the products I know. You have a cuspated sheet, so it's a formed plastic sheet, which can be rolled into a roll, which is very common in North America in all building construction. I'm sure in Australia it's the same. So these cuspated sheets offer very interesting properties as well, a very, very thick cavity. They have a very good drainage capability. There are some features which are specific to these products. You have structured geomembranes. That's another one. Some geomembrane are extruded in a way that's going to deliver a complex structure, which is going to preserve cavity when installed between 2 geomembranes or against a concrete wall. So that's 6 among the most common drainage structure which are available on the market. Now let's review a few of the key applications, a few examples. First one would be the roadway. Drainage blanket, which is installed beneath a road foundation. will obviously offer a drainage layer. It's going to capture the water seeping through the road base and transport it away to avoid bearing capacity losses. But an open structure like a geonet geocomposite installed under a road foundation at some depth can also preserve the foundation from moisture increase caused by capillary uptake. So when you so it can offer also a capillary break under road foundations. Retaining walls, so an undrained soil, backfill soil behind a wall can apply a load 2 to 3 times higher than when it's drained. So that's a coefficient of pressure, earth pressure at rest, which is basically highly dependent on the water content. And the next one, double lining system. So I think from what I've heard, double lining system is not a solution which is very common in Australia. It is very common in North America. It's a very classic structure for lining system for landfills in particular. So in these structures, the drainage layer is often called, the secondary drainage layer, the one which is installed between the two geomembranes, is often called the leak detection layer. And I think that's probably a description which should be reconsidered. It is indeed a leak detection layer, but the primary function of this layer is to reduce the water head that can apply on the primary liner. When you have a single liner and you have a water head of, let's say, 30 centimeters, which is a very common requirement for the regulations, when you have a 30 centimeters water head on the primary liner, it's going to drive some flow rate through a potential hole through the liner. Now, if you have two liners superimposed and a drainage layer, a functional drainage layer in between, you're going to basically reduce the water head on the secondary liner. And by doing so, you will also reduce the flow into the environment through the secondary liner. So a secondary drainage layer installed between two geomembranes for lining application is actually much more than a leak detection layer. And I think that's something that should really be considered on the Australian market. Right now, it's only a single liner for most of the application I've seen. And really, that's something that people should look at in Australia. Final closure of landfills, any capping application will require to have a drainage. In that case, the drainage is obviously must be able to capture the rainfalls, but a lot of the design will be related to the veneer stability. So we have here, for this application, we often have relatively high flows, which are calculated, and relatively steep slopes. The steeper the slope, the more material is under the liner. And with that, it's an interesting condition for design. Biogas management. So when you have organic material which are under a liner, very often they're going to generate methane and carbon dioxide. And to avoid uplift of the liner, which could also create its own lot of issues, you install a drainage layer under the liner. So it's not draining the water, it's draining the gases which are generated by organic materials under the liner. And in that case, the drainage layer is going to have an impact on the stability of the system and also on the potential for valorization of the biogases. The more gases you can collect, the more valorization you can do, and so on. In some cases, there is also applications for bioreactors for leachate recirculation. So still in MSW landfill, municipal solid waste. There are some experience with the use of geocomposite to re-inject, recirculate the leachate into the landfill, and that increase the generation of biogas, and in particular methane, and that increase at first the degradation of the waste until it reaches stable condition. Second, emission of biogas, which can be used for valorization, for energy production. So that's also an application which can be used with geocomposite drains. heap leach pads in mining. So the ore, after the first treatment, very often there is still a remaining fraction of the metal which is in the ore, and strong acids or strong bases are injected on the ore, and that will have an impact, and this acid will dissolve the metal and will take and the drainage composite will have to drain away the acid full of dissolved metal for further treatment. So in that case, the drainage layer is a crucial component of the process. It collects basically the resource from these pads. Tunnels, drainage layer are installed between the liner, between the concrete, to avoid disturbance and maintain the properties of the concrete on the long run. Building foundations. So now in North America, at least in Canada, the National Building Code has made it mandatory to have a drainage layer or a dam-proofing layer around every new building in residential constructions. So every residential construction in Canada must have a dam-proofing or drainage layer, which is typically cuspated sheets with or without fabric, to preserve the concrete from being in direct contact with the soil and to drain the water that could come from the soil toward the building. So how do we do to reach a good performance with these products? So now we're getting into the core of the presentation. First, the goal we have when we do the design of a drainage geocomposite is to maintain the waterhead within the thickness of the drainage geocomposite. That's the most common requirement for gravity drainage. I'm using here the example of veneer stability of a veneer on a capping. In that case, you see the rain which is falling on the soil veneer. The water is percolating through the soil veneer, reaches the geocomposite, and the geocomposite must have a sufficient capacity so that the water head within the geocomposite is smaller than the thickness of the geocomposite. That's a typical criteria. So when this is converted into measurements, which are technical measurements, which are specific to the product, that means that the flow capacity of the geocomposite must always be higher than the flow that may eventually reach this geocomposite. So these parameters are controlled by the rain, angle of the slope, length of the slope, and obviously the transmissivity or flow capacity of the geocomposite. When you don't meet these criteria, what happens is that you have the geocomposite which gets saturated, and you start to have, so it's reached its full capacity at some point, and then you start to have some water percolating into the soil. And at some point, the pressure of water into the soil will be greater at the interface, maybe greater than the normal load and the shear resistance of this piece of soil here, and that can lead to a slippage of the soil veneer, or you can simply have erosion of the soil veneer. So that's what happens. Here you had a situation where lots of erosion took place into the soil because the drainage was not sufficient. So to address the design, to be able to design geocomposite drains, there's been some code and standards that were developed. The first one that I know was in 2001. The Geosynthetic Institute published the GRI GC8, determination of the allowable flow rate of a drainage geocomposite. This was followed by an ASTM standard, which is taking a lot of this GRI specification, but which turned it into a little bit more comprehensive document, ASTM D7131. And in 2020, another document was published by the ISO 18228-4, Design Using Geosynthetics, Part 4, Drainage. So this effort, I'm going to make a small parenthesis, this ISO 18228-4 is part of a series of 10 design guidance which are published by the ISO Committee on Geosynthetics, ISO TC221. Part number 4 is on drainage, part number 3 is on filtration, part number 2 is on separation, I don't remember all of them. Part number 5 is on stabilization, part number 7 on reinforcement, part number 9 on lining, and so on and so on. So there is 10 different documents which are going to be published. The first ones to be published and available for the market are number 3 and number 1, 2, 3, and 4. Number 1, which is general consideration, number 2, separation, number 3, filtration, and number 4, drainage. This one will be published during the year 2020, unless it's postponed because of coronavirus situation. But normally it should be out for public on the market during the current year. In all of these documents, so they may be ASTM, which is very strongly influenced by the American philosophy. It may be GRI, it may be ISO, which is very strongly influenced by the European philosophy. All of them have in common the strategy, which is to compare the allowable flow rate provided by the geocomposite. And here, actually, I realized that I wrote the equation in the wrong direction. It should be the required flow rate divided by the allowable flow rate. And it should be always, sorry, it's correct. Allowable flow rate must be higher than the required flow rate. So the safety factor must always be greater than 1, which is what I explained a bit earlier as well. So how are these flow rates defined? The required flow rate, it's something which is defined by the project. It's a rainfall, it's a slope, it's the length between the collectors and stuff like that. This is not something I'm going to discuss today. It is actually discussed pretty extensively in the ISO 18228 document, but that's not something I'm going to discuss today. The allowable flow rate, on the other hand, is what we're going to discuss today. So here you can see that it includes the Phi100, which is transitivity at 100 hours, the short term, which is at the end the short-term flow capacity of the geocomposite, which must be measured with representative boundary conditions, and we're going to go through that after. And this value is divided by reduction factor. So it's not the safety factor, it's reduction factor, which take into account the different potential cause of reduction of flow because of the service condition. So we have the first one is reduction factor for creep deformation. Any polymeric material will creep eventually under load. And so there is one reduction factor for it. Then there is a reduction factor for chemical clogging, for biological clogging, another one for geotextile intrusion, and the last one for laboratory uncertainties. And so you see that the first 3 reduction factors were defined since the early 2000s by Geosynthetic Institute. So GRI means Geosynthetic Research Institute, and it was eventually renamed the Geosynthetic Institute. Then all these reduction factors plus geotextile intrusion were republished in D7931, and eventually the latest ISO standard incorporated as well another factor for laboratory uncertainties. So yeah, at the end, to be able to perform the design of a drainage geocomposite, we need basically 3 group of information. First one, what is the required flow capacity, which is defined by the project. Second, what is the short-term flow capacity of a product or transmissivity. And finally, reduction factors, which are specific to the product and the project. And we're going to discuss that now. So first thing first, determining the flow capacity QA or short-term transmissivity tau A of the geocomposite. There are 2 test methods which are available and commonly used in the market. First one is ASTM D4716, and the second one is ISO 18958. Both of them were developed considering that the flow, well, the test is the ASTM, sorry. the ASTM test was developed considering that the transmissivity is a value which is equal to the flow per unit width divided by the gradient, which means it considers that the flow follows a similar regime as Darcy's law in soils, that the flow is proportional to the gradient. And we'll see after that this may not be correct. But anyway, that's how it was developed. So you can see the transmissivity, which is the way the test, sorry, I'm coming back on the screen. The transmissivity is determined with the specimen installed under a piston, so we can control the boundary condition and the normal load. And we set water head difference between the upstream and downstream side of the geocomposite. And we measure the flow of water through this system. And that allows determination of the flow under a given gradient, under a given boundary condition, given normal load, and the sitting time. So again, geosynthetic can creep. They are polymeric materials. So the longer we're going to wait to do a measurement, the lower in some cases. Sometimes it's similar, but sometimes it's lower flow we're going to get out of the product. Now, what was observed? So when we are working with this theoretical consideration, considering that the flow is proportional to the gradient, that's how we define the transmissivity. But practically, doing more and more tests, we realized that for most geocomposites, the flow is not proportional, and there is in fact a relation which is more to the half degree. So the blue line here shows the relation between hydraulic gradient and flow rate for a soil, and the red line shows what we observe for geocomposites. So it's this relation here. When we convert to transmissivity, the relation is even worse. The problem is that we can have like 1 order of magnitude of difference depending on the gradient. What is a common rule of thumb for the relation between the transmissivity and the hydraulic gradient is that when you increase the gradient by 2 orders of magnitude, you're going to increase the transmissivity by only 1 order of magnitude. So that's the same as this function, this equation here. Another factor which is influencing the transmissivity is the normal load. So again, the products are compressible. There is a geotextile on top of the core. The geotextile is maybe covered by a soil. The more pressure we apply, the more compression we have and the less flow. So the more we increase the normal load, the more we decrease the flow. And transmissivity is the same. And you see that this relation is nothing but linear. So overall, when you look at the hydraulic gradient and normal load, when we increase the hydraulic gradient, we decrease the transmissivity. When we increase the normal load, we also decrease the transmissivity. So a typical example, don't look at the numbers, they're just for illustration. You can see that for the same product, you can have for a given hydraulic gradient a value which is here under 500 kPa. Under a gradient of 1, you have 1, 2, 3, 4 as a 4 times 4 for the transmissivity. And when you go to something closer to 20, 25 kPa and a much lower gradient, 0.1, you can have a value which is 5 times higher, 2 times 3. So that's how wide apart can be the transmissivity. For that reason, many people actually don't like to use this transmissivity value. In Europe, they always use the flow, the actual flow measurement to qualify geosynthetics. While in North America, we still use the transmissivity. Another factor which is influencing the behavior of the geocomposite is going to be the type of core. When you have a biplanar geonet with a traditional structure, which are relatively high, you can see on the left here, these products can eventually compress at, there can be a rollover, it's called a rollover of the ribs, which means that instead of being in a high position, in a vertical or close to vertical position, the ribs can fall and lay flat basically on the product. And that creates a significant loss of flow capacity at a given load. So you can see here on the compression, on the compressive stress versus compression of the product, the conventional strands can see a very large reduction of thickness at a given stress, while some other products with a different structure can resist much higher stresses. Again, another example of the influence of the structure. Here you can see the relation between the normal pressure and the transmissivity of three different products. The one that suffers the most reduction of flow capacity is a biplanar geocomposite. You have another one, biplanar standard geocomposite. Then the second one, Siamak, I don't know if you can help me. Do you see my mouse or not?
Yes, we can see that.
Okay, very good. So the one that you can see here, it's the biplanar geocomposite with the cylindrical structure. So here, that's this product here. The first one in the bottom is this one. The second one is this one. And the third one, which offers the best, the most stable behavior under quite high loads, here you can see that we're going up to almost 2000 kPa, is a triplanar geonet. So really every product, every structure will behave very differently with regard to the normal load. Another factor is the influence of the boundary condition on the geotextile intrusion. So when you have a geocomposite which is installed between two rigid products, like two geomembranes, for example, or against a concrete slab, the flow, the void which is available between the two fabrics within the thickness of the core will be the maximum. If you have soil on one side, the voids which are available between the thickness of which is available for flow between the two geotextile is going to be reduced on one side only, which leaves some, which still leaves some flow circulation. Last situation, when you have a soft boundary, that's when you have the maximum geotextile intrusion between in the core, and that gives the minimum flow capacity for pretty much all products. So examples here on how the core of a product can affect the flow capacity. You can see here on top a biplanar, a thin biplanar geocomposite between two geotextile and two soil layer. And you can see that basically there is not much space available anymore for flow. So this product, if it were tested between two rigid plates, would deliver some level of performance. When tested between two layers of soils, is going to give a completely different level of performance. So not only the stress, but also the boundary condition are going to influence tremendously the flow capacity. This behavior is not true for all products. Like if you look at the box type geocomposite, like what is illustrated here, these products have a much better performance with respect to geotextile intrusion. So here, well, you can see it visually. The difference, the flow you're going to get between two rigid boundaries or two soft boundaries is going to be a little bit different, but it's not going to be tremendously different as it is for the biplanar geomet here. So these products can be extremely interesting for performing when you have soil in contact with the fabric. So these sound like we should always use boxed product and triplanar geonet because they offer the best performance. Actually, that's something that you should design, because if you look at the structure of these products, the triplanar geocomposites are going to have a very high orientation, which means the flow in a perpendicular direction in the direction perpendicular to the ribs, to the main ribs, will be extremely slow. It's extremely small. on a project which was published in the early 2000s here, some publications show that it's less than 20% of the flow that goes perpendicular to the ribs for a triplanar geocomposite, while with a biplanar geocomposite, you still have almost 40%, so that makes a big difference. What is a practical consequence of that is the installation of the geocomposite. When you have a triplanar geocomposite, you must follow the slope exactly, or as close as possible, stay as close as possible to the main direction of the slope. Otherwise, you're going to have some, you're going to have more turbulence. You're going to have a flow which is not going to be optimum, and you're going to lose some capacity because of that. So, so it doesn't mean that they are not good. It means that there are some more attention to give at the stage of installation for triplanar geocomposite compared to biplanar. Biplanar is more tolerant. It has less flow, but it's more tolerant. Another factor is the seating time. So my graph here could suggest that it can be completely dramatic. No, usually the seating time actually, we're going to see some significant difference between measurement taken after a few minutes, after 15 minutes, after 1 hour, than what they're going to be after 24 hours or 100 hours. Some the quantity of data which is available in North America with tests up to 100 hours allows to make educated guess, let's say. And what we are observing is that after 24 hours, the change of transmittivity is relatively moderate. The industry has established that 100 hours should be the sitting time to be used for design in GRI GC8. That was, again, 20 years ago. And we are still using this number for design because it is much less sensitive to the time. If the measurement is done after 100 hours or after 102 hours, or if it's done at 98 hours, it's going to be pretty much the same. It's a much more consistent, more repeatable number, which is thus much more reliable. When the test is done with a very small sitting time, we have a much higher chance of not being behind the primary creep, which means there could be significant changes of transmittivity. So that is a relatively controversial topic between the European approach and the North American approach, because in Europe, the sitting time is 6 minutes only. And in North America, I don't think anybody tests below 15 minutes. And for design, it's going to be 100 hours as the baseline, and some people go down to 24 hours or 1 hour. Well, it depends. But the typical numbers are much, much longer with respect to the sitting time. So in summary, if we look at the factors influencing the in-plane flow capacity or the transmittivity of a geocomposite, the hydraulic gradient, the normal load, the boundary conditions, and the sitting time are going to be critical factors that must be defined to obtain a value that has a meaning. You cannot use a value which was measured between two rigid plates and consider it can be modified to get a number that can be used for when the boundaries are soil or something else. So it's really values which are specific to these boundary conditions, normal load, sitting time, and so on. And the test may be performed by either ASTM 4716 or 12958. As I said, transmittivity for D4716 and in-plane water flow capacity for the ISO. So now I'm going to make a quick description of the main difference between the two methods. ISO 12958 is a test which was developed quite some time ago. Actually, I don't remember when it was developed exactly, but the last revision before 2020 was in 2010. So the way it was, so there was some revisions in 2020, and I'm going to describe what's the new test, which is again being published. It's going to be out in the next couple of months. So in the historical standard, we had 3 normal loads that were predefined, 20, 100, and 200 kPa. we had hydraulic gradients of 0.1 and 1, and the test was also requiring to use closed cell foams as boundary conditions, so to maximize geotextile intrusion into the core and minimize the flow capacity. And the sitting time, again, was 360 seconds. What was done in 2020 to accommodate the design strategy, and in particular the ISO 18228-4 that I mentioned earlier, a new performance test was developed, ISO 12958-2. And for this test, we are getting much closer to test conditions which are relevant for design. So the normal load is according to the project specification, to the service load. Hydraulic gradients should also be defined according to the service conditions. Boundary conditions also are according to the project specification. A standard sand is described because it's always good in standards to have a repeatable value, but it's also possible to use a standard sand. The site specific soil. And for the sitting times, we're increasing a lot from 360 seconds to 100 hours. So now what used to be one standard for ISO with only standard laboratory specific test condition, focusing a lot on repeatability. Now we have two standards, one which is doing exactly the same as before, and a second one which is going to be focused on performance. Another important factor for the ISO 12958 standards is the width of the specimen. ISO 12958 allows for a width of 300 millimeters, like in ASTM, but the minimum width is actually 200 millimeters, and that may affect in some cases, for some products, it may affect the measured properties. Now, if we look at ASTM D4716 is a very open testing strategy. It provides some guidance for the selection of test conditions, and it can be used for performance testing and MQC. Something I forgot to mention actually before is that in ISO 12958, the standard test, which requires only 6 minutes of sitting time with very precise and repeatable test conditions, is extremely convenient for MQC. So it's not something which is bad. It's just like when you test transmissivity, you have to differentiate testing for design and testing for MQC. And that's not the same philosophy of work. And testing for MQC, for manufacturing quality control, with a 100-hour sitting time means that when you're finishing the test, the production is finished, is rolled, and is shipped. And so that cannot work really for MQC. So we need something very quick, very, very easy to run. So that's the reason why we still have this transmissivity test in ISO 12958 and in ASTM as well. So this 360 seconds sitting time is there for a reason. ASTM D4716, so we have two, again, I'm differentiating two different approaches. One, which is the MQC. And what we see is the most often in standard specification for manufacturers is normal loads, which are going to be anywhere between 500 and 1000 kPa. I should actually say 10,000 PSF up to 20,000 PSF, which is what is usually published. So 10,000 PSF, 15,000 PSF, and 20,000 PSF. Most of the manufacturers are going to specify their products according to these normal loads, despite the standard is proposing as a default normal load something completely different. So for MQC, again, we're going to have hydraulic gradients of 0.1 or 1, which are going to be the typical values. The boundary conditions are going to be either rigid or closed cell EPDM foam. But I have to say it's not often that I see something different than rigid boundary condition, just because it's easier to run in the lab. It's basically the piston applied directly on the product, and there is no foam which can age, which has to be replaced, and so on. So it's easier to run, and also, of course, it gives a much higher flow capacity. So on the spec, it looks much better. And finally, sitting time, which is 15 minutes in ASTM D4716. People seem to be happy with that, but in some cases, I have to say, even 15 minutes is a bit short. It's convenient for MQC, but if you look at the practical way of running the test, let's say you start after 15 minutes to do a flow measurement, you're going to end the first series of flow after 17, 18 minutes. Then you're going to run another series of flow measurements. You're going to be at 20, 25 minutes. And during these 5 or 10 minutes after 15 minutes, you can still have some flow reduction. Never as bad as or as big as in with the ISO requirement for 6 minutes, but you do have some changes of flow, and that also depends on the product and so on and so on. Finally, the typical testing condition for performance testing. So in ASTM, again, it's very, very open. The only thing that I realized has to be reconsidered, and to be honest, I did communicate with the person in charge of this test at ASTM and mentioned that, and hopefully we're going to work on that in the coming month. The sitting time for the performance test should be selected considering compression test data of the product to be tested. So I've been 25 years in this industry, and I noticed that only this week. Because practically everybody is using the same standard sitting times of either 15 minutes or 100 hours. So that's the basic description for ASTM D4716. So what are the main difference between the two, ISO and ASTM? ISO 12958, the normal load is typically relatively low, 20, 100, and 200 kPa. And for ASTM D4716, what we see the most often are either similar type of loads, like low loads, 50 kPa is very common. I mean, 1000 PSF in North America. And so for the products which are intended to be used with relatively shallow depth of soil on top of them, often they're tested at 50 kPa. And when it's for basal liners and high loads, what we see the most often is 500, 750, or 1000 kPas. Hydraulic gradients are 0.1 and 1 under ISO. And what we see often in ASTM D4760s is the same, 0.1 and 1, but also we see sometimes 0.02 for hydraulic gradients. These are much more complex to control in the lab because 0.02 gradient for a 30 centimeters long specimen, that means 6 millimeter water head. And to have a good control of these 6 millimeters water head, you need to have a very precise type of equipment. So it's not everybody who can do it. But when you can have a good accuracy on the control of the hydraulic gradient, with the information I've presented you before, you realize that the measured transmissivity is going to be much higher. So using a very low gradient, 0.02, is good in the sense, good for specification, in the sense that it shows very high numbers for transmissivity. Boundary condition, the new standard, actually what I've written here may be confusing. Here I've written that the current specification calls for it. That's true. You do have most of the boundary condition in the current specification, which are rigid, and sometimes rigid soft and soft soft. But in the new, this does not exist in the rigid soft and rigid do not exist in the 2010 specification. It's only soft soft. So the 2020 version of ISO 12958 will include all these boundary conditions, which reflects the current situation on the market. On the other side, what we see is the most often for manufacturing quality control and construction quality control for ASTM D4716 is really rigid. I don't recall seeing for MQC the use of soft boundary conditions. And the last difference between the two methods is really the sitting time, 6 minutes for 12958 and 15 minutes for ASTM D4716. I realize that I'm spending way too much time. It's already 11 o'clock your time. 20. So that's the biggest difference between the two tests. For the performance testing from 2020 and going further, so we do have two test methods. Both solutions are available with both standards. Yeah, voila. So to make a long story short, with the overall, the two methods are similar, except again for the sitting time. Now let's go to the most important part actually. So reduction factors. Again, we have 5 reduction factors which are needed to control to perform a proper design for a geocomposite. So we're going to go through that. These 5 reduction factors, if you look at how important they are in terms of design, the cumulative, the product of all these reduction factors can be as high as 35, which means depending on the values you're going to get, you can have theoretically 1. It's never 1, it's always more than that. But theoretically, you could have a reduction factor of 1 or of 35, depending on the condition you're going to consider. The most important being the creep reduction factor. So some products can require a reduction factor of 6 or sometimes more, I'm sure, which is going to make a tremendous difference. First one, the easiest, because we spoke of it already, geotextile intrusion is going to depend on the structure of the core. Theoretically, well, practically, there is not much data available for this reduction factor because we consider the geotextile intrusion for the initial transmissivity test, and this reduction factor should apply to what is developing after the initial transmissivity test. So very often it's neglected, to be honest with you, or an arbitrary number. I don't know any manufacturer who was actually publishing this value.
Sorry, Eric.
Yes? We're
almost running out of time for the Zoom webinar. So, and yeah, I've received probably more than 20 questions. I really want to get to those questions as well, if we can just.
Okay, so I'll try to be quicker. Biological clogging, I have, I think, something like 10 or 10, 15 slides still, and that actually that's the most important. Give me 5 minutes. I'll try to go through in 5 minutes. It's okay?
Yep, good.
Okay, thank you. Biological clogging. So biological can, when you're draining organic leachate, like a leachate from a municipal solid waste landfill, you can have biomass developing, you can have some biological activity developing, you can have some roots developing into the product, and this needs to be addressed. So GRI GC8 has published a number of reduction factors which are very commonly used in the industry. It goes from 1 to 3.5 for landfill caps. You will see that in landfill leak detection layers, it's actually lower than in landfill caps. And if maybe in the question time, we can discuss that further. However, one thing which is important is that there is no test method currently available for this determination. So these reduction factors have been used for the last 20 years. To my knowledge, it works relatively well. However, I would like to mention that I did contribute to a publication which was questioning the relevance of these numbers for some application and for some products. So in 2012, I did question that, and we observed that based on experimental observation, we observed that values between 2.6 and more than 10 would have been more appropriate depending on the structure of the product. For example, a geonet without any geotextile is going to have a much higher resistance to biological clogging. It's going to be much less sensitive than when there is a geotextile. Also, there is a question of conditions, if it's aerobic, anaerobic, and so on. So we did a quite in-depth investigation of the clogging of geocomposites and brought some numbers for reduction factors. The next question being, what do we actually need in terms of flow in the landfill? Because the more you increase the waste height on the landfill, the less water or leachate actually reaches the drainage layer. So after construction, that's mostly rain. You can see here, right after construction, it's mostly rain. But then the more you increase, so rain has no biological activity at all. So you don't need to have any reduction factor for clogging. The more you increase the quantity of leachate into the landfill, the more you have some leachate actually reaching the drainage collection layer, but the less flow you have getting there. So the less need you have as well. And eventually, when you install a cover, a geomembrane, some numbers were published about 10 years ago, suggesting that 0.2% of the initial flow would be a reasonable target. So basically, we have a 500 reduction factor or safety factor after cover of the geomembrane. So that's why we have to really have a weighted approach on clogging resistance. And again, GRI GC8 appears to work relatively well after 20 years of operation. I'm not aware of any problem. Maybe there are, but I'm not aware. Creep now. So any polymeric material will creep when exposed to a constant stress. There is a procedure which is proposed in ISO 18228-4 for the determination of the reduction factor. What does it do? It requires to have to control, to know what is the creep deformation of a product under the service load. It requires to have a short-term compressive stress data for the product being investigated. And then with that, we can perform a short-term flow test under representative conditions. This standard also provides some typical lifetimes for the determination of the creep reduction factor, which are between 1 and more than 100 years, depending on the structure. And you see here, landfills is 30 to 50 years. And that, again, because once there is a cap on the landfill, when it's closed, the quantity of liquid circulating there is minimum. So how does it do, this test? Once we know the relation between time and thickness, we can define for a given lifetime of a project a value of residual thickness under rigid boundaries. From there, we go to the short-term compressive test and define what is the pressure we would get on a new product to go down to this thickness here. Once we know this pressure, we perform a hydraulic test, so a flow capacity test under service load, service gradient, and representative boundaries for the project. And that gives us a reduction factor for creep. So that gives us a flow capacity. And from this flow capacity, we can determine the reduction factor or use that directly as a reduced flow and add to it the other reduction factors. So how do we get these numbers? The most important value to obtain here, because these are short-term tests which are quite easy to do. This test takes like 1 hour, and this test takes the same 1 hour. This one is a more complex test, the creep test. So first method is ASTM D4706, test method for time-dependent compressive deformation under constant pressure. So basically what we do, we apply a load on a product and we measure the deformation and we wait and we wait. The problem is that this test is not accelerated, so it is extremely long. 10,000 hours, which is a common target value, requires more than a year to reach. So that means it's not really convenient, and also it's completely impossible to test up to service life. So for that reason, there is an accelerated creep test which exists, ASTM D7361. And in that test procedure, it's possible within 24 hours to project the compressive behavior of a product up to 100 hours. The way we do it is that we increase the temperature regularly. Every time we reach a straight line, every time we enter the secondary creep of the product, we increase the temperature, and that creates an acceleration. And we can, I'm not going to go into detail, but we can project basically, we can bring together all these numbers and develop thickness versus log of time relation to be able to project to, that should be 1 year actually, 25 years or 120 years. Some values are published in ISO 18228-4, and you can see here for that kind of product, geomat, the values which are proposed go from 1 to 6. So that means depending on the test condition, applied pressure, and lifetime, you're going to have tremendously different reduction factor for the product. You see here under 500 kPa, you go from 220, 230 up to 6. So that's a huge difference. Quick parenthesis is the influence of tangent stress, which can also be considered. This is not covered in the ISO method. It's only mentioned that it exists. But when you have a biplanar, some products are more sensitive to tangential stress than others. So a biplanar geonet, for example, can experience rollover. And this series of experiments here were reported in this paper. And you can see that the ribs, the vertical ribs at some point were basically rolling down and creating this, this failure of the product. So a product that was performing better in some way than in the beginning, after some time, after here 1,000 hours, it would fail and break completely. So we need to understand this this aspect. So in the BAM in Germany has published all this data and is proposing a relation between the normal stress, the tangential shear stress, and the flow capacity. So you can see that there is a complex relation between these factors, and that can affect tremendously the reduction factor for creep to be considered. So examples of reduction factor for different type of products. So here for geomat, that's the one that's the values which are published in the ISO standard from 1 to 6. For biplanar geonet, you can see here reduction factors that can go, which are around 1.3 for a 300 mils product. For a rounded strand geonet, so it's a different type of structure which is less sensitive to rollover. We're going to reduce these reduction factors to 1.1, which is very good. Triplanar at high temperature and much higher load, we're still around 1.1. Box type, which is this kind of structure, you're all again at 1.1, 40 Celsius. And there is one product I want to mention. It's a tubular drainage composite. So in that case, we have a pipe, basically a pipe, that it is illustrated here. And a pipe, when it's completely confined between two layers of soil, is not going to creep at all. So that's an interesting structure with respect to the creep behavior. So overall, we have the short-term flow capacity, transmissivity, which depends on the structure of the product, on the boundary conditions, on the normal load, on the hydraulic gradient, and on the sealing type. The long-term performance is going to depend, of course, on the short-term flow capacity, on the creep deformation, and on the biological and chemical clogging. So that's basically what the message I wanted to convey. What I have not covered in this presentation is the viscosity of the liquid, which may in some case affect the performance. Dynamic and cyclic loading, it may bring another set of consideration. any extreme project. So if we're working with 2000 kPa with extremely high temperature or whatever, that's a different story as well. Polymer aging, that's also something which is which probably needs to be improved in the coming years for geocomposite. I've seen a few projects where OIT and stress cracking resistance were specified for the polymer, but it's not the majority by far. And another thing is the use of geonet geocomposites as capillary breaks. I've mentioned it for roadways, but I've not developed that at all. It's a different fish, completely different fish. Other relevant design concerns, there is durability and UV resistance of the geotextile. That's something which must be specified as well. Filtration properties, you must select the geotextile according to its filtration properties, considering what's in contact with the fabric. Veneer stability, interface, shear strength properties, also there is a complete science on that with how to test and where to test. Gravel puncture, I've mentioned it, but again, it's another group of information which has to be dealt with. And to conclude, 15 minutes behind schedule, I'm sorry about that. Drainage geocomposites are really offering a better solution than gravel for consistency, performance, sustainability. I hope we don't see that soon, but I hope that our kids don't have to deal with that. But sustainability, availability of sand, of gravel material is something that should eventually be considered in projects. Greenhouse carbon emission and so on. Voila, so that's really the message I wanted to convey. And here I've provided a list of information. Siamak, you mentioned the IGS webpage and what's available for IGS members. I want to emphasize on the photo library, which is in the IGS, which is very interesting. It showcases a lot of really nice projects around the world. It's not limited to one region. It's really a very nice group of photos. There is also lots of training documents which are available on the IGS webpage. So I really want to put some emphasis on that. And now you mentioned that maybe there are some questions.
Yes. Thanks, Eric. If you could please just stop share so I can see the question tab.
Yes.
Well, we have 36 questions that I have received. We won't get through all of them. With the time that we have, I would probably ask 3 or maximum 4.
I'm there for the rest of the night for me. So it's really a question of how you want to deal with it.
Yeah, so I can email the rest of those questions to get the answers. So one question about immersion testing with elevated temperatures on GCDs to assess long-term durability in aggressive, such as highly oxidative liquors or soils. Has this been done, and how well established are the geonets in comparison to geomembranes in that application?
Okay, I actually mentioned just a little bit earlier that addressing the polymer chemistry, the durability of the polymer is something which is starting to be seen in specification. And at the end, to my knowledge, the industry will typically follow the request of the customers. So if you don't ask for it, you will not get it. If you ask for it and there is a project going with it, I'm pretty sure that you'll get some answers.
Yeah, good. For landfill gas drainage, do you have any comments on gas permeability?
If I may add another thing, with respect to the flow capacity under high temperature, a really nice thing that is possible to do with the SIM testing, with the accelerated creep tests for compression, to define the reduction factor for creep, is you can use different temperature. You don't need to work only at 20 Celsius. You can project the behavior of the product at a much higher temperature than 20 Celsius. So that's something which is addressed with the flow capacity. Yep.
Landfill gas drainage. Do you have any comments on gas permeability of the geotextile layers in a geocomposite drain if the geotextile becomes moist or wet?
Well, that's a good point. No, I don't have any particular knowledge about that. The only thing I can say is that if you look at the quantity of gas that goes through the fabric for a landfill, for gas drainage layer, if you look at the quantity of gas that's going to enter the fabric, and if you have 100 meters long system, that means there is 1% of the flow going through the core that's going to go through the fabric over the first meter or over any meter. That is usually the bottleneck is not on the permeability of the fabric, it's really on the transmissivity of the core, for what I know. It's a project specific, of course, but to what I know, the bottleneck is the transmissivity, it's not the permeability.
Okay, another one, your opinion about geocomposite drains considered as a good cushion layer for geomembrane if they use as in a composite application.
Indeed. It's going to depend on the type of geotextile you're going to use, of course, because when you have a composite drain, you have like 5, 6, 8, 10 millimeters thick spacer. Basically, it's a spacer. And you have 2 geotextiles, one on each side. There's a typical structure for a composite. And when you're working on a geomembrane, usually you're going to have that. So that means you're going to have to select the geotextile, which is between the ribs of the geonet and the geomembrane, in such a way that it's not, the ribs are not going to go through the geomembrane. Very often, the density of the ribs are a little bit higher than the geomembrane. They're the same or higher. When they're higher, that means there can be a puncture taking place. So you need the fabric there to avoid puncturing the membrane. When the density of the net is the same as the one of the membrane, then you don't have any interaction, which is problematic. The one is not puncturing the other. They are only one next to the other. One.
Yep.
It's not the same problem.
Next one. Peel numbers for geocomposite strip drains, geocomposite drains.
I'm sorry, can you repeat?
Peel strength numbers, how important are they?
Extremely important, in my opinion. At the last conference, when was it again? It was in Houston in February, I think. You have an excellent paper by Rick Till that I highly recommend to read. He's proposing a very complex strategy for quality control. It may bring quite some complexity in the field, but I think it's good to read it to understand how important it is to have to control the peel strength. To make a long story short, it is for a geonet geocomposite, it's normal. I don't know any product on the market which is completely welded on 100% of the surface. There is always, it is not possible to have 100% of the width perfectly welded on all the length because of the technique which is used. So you will always have some pockets here and there where the fabric is not going to be properly adhered, and we're going to have some low peel strength. Rick Till has done some expertise in the past, and he observed some failures, and he did a lot of investigation. I really appreciate Rick's work. And he realized that when these products are sent to the lab for QC, the lab is not going to test the regions which are not adhered. And with that, they're going to select a region where there is an adhesion, which means they're completely avoiding all the pockets which are not adhered. And he's proposing a criteria on the percentage of the surface which is adhered versus non-adhered. And that facilitates, that permits to do some calculation, and he's bringing some criteria on how to make things work with respect to the shear strength properties and the shear stress which exists on the project. So yeah, it's a very interesting discussion. I'll be happy to discuss that further. Again, it is not possible to have 100% of the surface connected, but there are some ways to address it.
Okay, and the last question about long-term performance of drainage geocomposite installed in contact with GCL. what do you think in relation to migration of bentonites in the GCD?
Maybe I'm missing something, but I don't see how it is different from installation against the soil. Or maybe you're talking of how the GCL is going to behave, not on the geocomposite.
I think it's more about migration of bentonite, like bentonite erosion sort of scenario.
Okay. I have to think of that question. I am not able to answer to you right now.
Okay.
Yeah. Other questions. Really, I'm available. It's really up to you.
Okay, no worries. Thanks a lot, Eric, and thank you to all more than 100. So we had only capacity for 100 attendees, and I was getting messages after we reached the capacity. A lot of other people wanted to join but couldn't because of the capacity of our platform at this stage. We will look into increasing that capacity for our future webinars. For those who sent me questions, so the number went up to 37 questions. I only had time to ask a few of those, but the rest of those questions I'll email them to Eric, and as soon as he sends me the answers, I'll forward to the people who asked the questions.
Yeah, we can entertain a discussion. I'll be happy to do that.
Okay, thanks very much, Eric, and thank you for attending this webinar, and we'll see you next month in our future webinar. Thank you all.
Thank you.